from AT&T Labs Research. Luna is actually a graduate from the University of Washington a few years back, and she's very well known for her work on personal information management, web search, information retrieval, and more. And today she'll talk about copy detection.
Thank you. Hi, everybody. It's very nice to come back. I just told Magda that 10 years back I landed at Seattle, and so I have been in the US for 10 years. And so today I'm going to present our Solomon project, where the goal is to find the truth via copying detection. So we live in an information era. There is a lot of information on the web, and we are surrounded by data. Especially after Web 2.0, we can easily know what's happening out there from social network websites, from Twitter, from blogs, so on and so forth. In a sense, we are lucky that when we have a question, we can just ask the web. However, a recent study by the British Library showed that the speed of young people's web searching means that little time is spent in evaluating information, either for relevance, accuracy, or authority. And actually, another study shows that a lot of teenagers thought that as far as a web page is listed by Yahoo search, it must be authoritative. But this is certainly not true. And as we know, there are a lot of low-quality information on the web, being imprecise, being erroneous, or out of date. And what makes it even worse is that the web technology has made it much easier to propagate such low-quality information. Everything is digital. There is certainly no need to talk face-to-face or making a phone calls. Spreading some rumors is as easy as making a copy. So low-quality information, rumors quickly spread out. So let me tell you several stories. The first story is an old one about United Airlines. So in 2002, Chicago Tribune has a news article about UA's bankruptcy. Then, a couple of years ago, SunSentinel.com, for some reason, listed this article as one of the most popular articles. And then, Google News Robot looked at this list and sent it to URL alerts clients. And after that, Bloomberg.com looked at the timestamp from Google News and listed as newswire confirmed today. So guess what? The URL stock jumped from $12 to $3. The second story is about a musician. His name is Jaha, and he's a French conductor and composer. He died 2 years ago. A lot of newspapers reported his death with the following quote: "One could say my life itself has been one long soundtrack. Music was my life, music brought me to life, and music is how I will be remembered long after I leave this life. When I die, there will be a final waltz playing in my head, and that only I can hear." So very touching, isn't it? But it was not said by Jaha. It was not said by any musician. It was said by an over-curious sociology college student who wants to know what's the impact of Wikipedia on people's daily life. So he uploaded these quotes after he heard of Jaha's death. And even he was shocked that a lot of quality newspapers with a very good reputation from North America, from British, from India, from Australia, quoted his words without verifying or even referencing it. So Wikipedia can spread rumors, and Twitter, which gains its popularity in the past couple of years, is a perfect place for rumor. So after the Japan earthquake and the tsunami, there have been a lot of rumors on Twitter about the toxic rain, about the death of some famous Japanese people, about some fake donation account. And this one is most creative. Please help Japan. Earthquake weapons caused the tsunami. And the final story happened recently. It is about Shirley Sherrod, who was an officer in the Georgia state. I guess some of you possibly still remember this. So last April, she gave a talk. And then last summer, Andrew Breitbart posted in his blog a video excerpt about her talk, showing that she once discriminated against a white farmer. And this is a big thing in this country. And so this video was quickly commented and included by some major newspaper websites. And this time, and then it is quickly picked up by the blogosphere and Twitter. This time, even the U.S. government was fooled. They called Shirley Sherritt and enforced her to resign. But after they look at the full video, they realized that Shirley actually did not discriminate. She actually even helped that white farmer. And eventually, Obama had to call her and apologize. So Obama said, we now live in this media culture where something goes up on YouTube or a blog, and everybody scrambles. And Tim Berners-Lee, the inventor of World Wide Web, said that the internet needs a way to help people separate rumor from real science. By the way, I got both quotes from the web, so you decide if you want to believe it. Okay, so copying can happen not only to texts, but also for some structured data. Here I'm showing 18 websites about US weather. And by investigating their websites about explicitly claimed partnership, resources, and clients, and by checking their code for citations, we found the following copying relationship. An arrow from A to B means that A copies the data or derives the data from B. So we see that most of the sources get their data directly or indirectly from weather.gov. In addition, such kind of copying can be large-scaled. Here I'm showing a map of about 900 data sources about books, book information. And we extracted that from appbooks.com, which was an aggregator of online bookstores. In this map, each node represents a bookstore, and that is data source. And an edge represents a copy relationship detected using our techniques. And we cluster the bookstores according to their copying relationships. So each cluster is represented by a country. And we did find some interesting countries. For example, this country, which we call Department Storia, has several department bookstores, such as Powell's Books, A1 Books, the Book.com. And this country, which we call Textbookistan, has several textbook stores, such as LGTextbooks.com, Textbooks Rus, Express Text, so on and so forth. So when we integrate data from all these different sources, we definitely want to be aware of such copying relationships so we can avoid being biased by the copied data. So for this purpose, we worked on this Solomon project. Solomon was a wise Israel king who is good at telling the truth from the false. And so the goal of our project is twofold. First, we want to discover copying relationships between structured data sources. And second, we want to leverage the detected copying to improve various aspects of data integration. There are certainly many other benefits of the detected copying. It can be used for business purposes. Data are valuable, and the data providers possibly want to protect their own rights. And we can use that for in-depth data analysis to understand how the information is disseminated and how the rumor is spread out. So the Solomon project has three components: copying discovery, applying the copying relationships in data integration, and visualization and decision explanation. In my talk, I will focus on the first component. I will briefly talk about the applications, and at the end, I will show a demo. Okay, so far so good? So when you have a question, interrupt me with no problem. Okay, So let's get started with copy detection, where we are considering a set of objects. Each represents a real-world entity. An object is described by a set of attributes. For each attribute, there is a single true value reflecting the real world. And our input is a set of data sources, each providing data for a subset of the objects. In our example, we have 4 data sources, each providing information for 2 books. We see that there are some missing values. There can be some incorrect values or partially correct values. Here, instead of Peter, it should be Pete, P-E-T-E. There can be different formats for the same value. Here we show 3 different formats of the same name. And actually, there are a lot of different formatting for author lists, as shown by this pie chart. So our goal is to find for each pair of sources the probability of one source copying directly from the other source, or vice versa. And here, a copier can copy all or a subset of the data from the original source. The copier can add some values or verify and modify some of the copied values. For all such values, we would consider them as independent contribution of the copier. A copier can also reformat some of the values, but those values are considered still as copied. So in this particular example, we see that S3 copies book 1 from S1. It copies book 2 from source 2. S4 copies from S3, but reformat the author lists. So there are many challenges in copy detection. First, sharing a lot of data in itself does not necessarily indicate copying. This is because 2 accurate sources can independently share a lot of correct values. Second, not sharing a lot of values in itself does not necessarily indicate no copying. A copier can copy only a small fraction of the data. Third, in many applications, we have only a snapshot of the data, so it is hard to decide which source is a copier. And finally, the copying relationship can be complex. There can be co-copying and transitive copying. In this example, S4 transitively copies from S1 and S2, but we want to distinguish that from direct copying. So the high-level intuitions for copy detection is this. If the probability of our observation of S1's data conditioned on S1 being a copier of S2 is much larger than the probability conditioned on S1 being independent of S2, then S1 is more likely to be a copier of S2 according to the Bayes rule. But when will this inequation happen? So first, this could happen when this part is very small. So if 2 sources share some data and the shared data are unpopular values or unpopular formats, and for example, it could be some incorrect values, then this part will be very small and copying is likely. To illustrate this, let's do a quiz. So let's consider 2 data sources that provide information about USA presidents. And ignore the formatting issue for now. I put them in the same format so you can easily compare. So we see that the 2 sources provide exactly the same lists. And they are actually all correct information. So do you think one has to be a copier of the other? No, because the 2 sources can both be accurate sources, and copying is not necessary. But how about this case? Again, we see a lot of shared data, although there are actually some different values. And we see that a lot of the shared values are actually incorrect. And what do you think this time? Yeah, so independently making a lot of common mistakes is a low probability event. So copying is likely here. The second intuition is that consider some values provided only by S1 but not by S2. Then, when we compute this probability, we use the profile of S1's own data. And when we compute this probability, we use the profile of S1's overall data. So if S1's data is inconsistent, then this inequation can hold. So in other words, if we have some property function of the data, such as the accuracy of the data, and if the property of the overlapping data is much more different from the property of S1's own data than from S2's own data, then copying is more likely from S1 to S2. S1 is more likely to be a copier, in other words. And this is how we decide the copy direction. Continue with our quiz. So now we see these two sources share some common mistakes, so copying is likely. And sorry, this is actually should be wrong values, false values. And we see that for S1's data, there are something correct, something wrong. But for S2's data, they are all incorrect. So which one do you think is a copier? How many people think S1? 1. How many people think S2? So the answer is actually S2. We see that the quality of S2's own data is very different from the quality of the shared data, which is half correct, half wrong. And so S2 might copy some of the data and then randomly guess the rest of the data. Yes?
I mean, my intuition though would be that if I'm copying from someone, I can only get better than them because maybe I can be copied from two different sources, you know. So I copy the data that I sort of have for some other reason, and notice that it is correct, and for the rest of the data, maybe, you know, I correct myself if I think the other source.
You actually are mentioning this case. So this is the second example where, again, we see a lot of copied data and a lot of shared common mistakes. And on the other hand, we see that S1's own data has very high accuracy, but S2's own data has very low accuracy, consistent with the rest of the data. And in this case, S1 looks more like a copier because of this inconsistency. So note that it is the inconsistency of S1's data rather than the accuracy of S1's data that tells us which one is the copier. Yes?
Because I am very confused by the intuition you're getting across here. It seems as if you're making some assumptions about the mechanism of copying and exactly how much information is going to get copied and whether one's going to copy from multiple sources and check, or whether one's going to copy and then randomly change values or try to, and without, you know, based on, I actually don't know in reality what people do copy.
We
I
actually,
imagine if they're going to copy, they probably copy an awful lot, but that's the intuition that I have. This seems, I don't get your intuition.
So I guess so first we don't assume that the copier will collect data from multiple sources, or the copier will randomly guess the rest of the data. So consider this case. One case is that the copier can copy the data and then randomly guess, or provides its own data. And then the property of its own data can often be different from the property of the copied data. On the other hand, the copier might copy the data and fix some of the errors. Recall that those fixed errors are considered as independent contribution of the copier. So the accuracy of the fixed data are typically higher than the accuracy of the copied data. So again, we see this inconsistency of the property of the copied data and the property of S1's own data. So rather than assuming some copying models or copying behaviors, copy patterns, we sort of consider, okay, so suppose this is the property of the overlapping data, and that is the property of the S1's own data. Then if we see inconsistency, we will suspect more that copying is happening. Otherwise, if the source just independently provide all of the data, inconsistency is less likely to happen.
Okay, just to verify that
Mm-hmm.
maybe I get this right.
Mm-hmm.
So you take the intersection of data that
Mm-hmm.
matches the both sources, and
Mm-hmm.
then for S1, if S1 is the one you're checking,
Mm-hmm.
you're taking the rest of the data.
Yes,
And
yeah.
you compute the portion of correct answers in the shared data versus
Mm-hmm.
the portion of correct answers in the non
Mm-hmm. Mm-hmm.
shared data. If
Mm-hmm.
those are close together, then you assume
Mm-hmm.
no copying is happening. If those do not.
Oh, if those does not happen, then we are less sure of the copy direction. But
Okay.
as far as a lot of wrong values are shared, we still consider copy is likely to happen.
I see.
Yes.
I see.
Yeah.
But if the portions, okay, so let's take the case where the ratio of
Mm-hmm.
how many correct
Mm-hmm.
answers I get is very
Mm-hmm.
different between the shared set versus
Mm-hmm.
the non-shared set.
Yes.
Does this always indicate copying in one direction or the other?
So it depends on how we compare this. So note that this is the difference of the property of the overlapping data and the property of S1's own data. And this is the difference of the property of the overlapping data and the property of S2's own data. So we compare this one. If this one is much larger than this one, then S1 is likely to be a copier.
But in practice, how do you know if it is correct or not? If you have this.
Yeah, that's a very good question. We will talk about that in the latter half of the talk. Yeah. So, any more questions so far? Yes?
Just to make sure.
Uh-huh.
What if they are both inconsistent?
If they are both inconsistent, then we are less sure.
So then it's possible that even though they share data, then none of them copies the same.
So if they share data and share a lot of common mistakes, then we consider it is very likely that we have some copying between the pair of sources. But on the other hand, if we didn't find inconsistency or we find inconsistency on both sides, then we will be less certain about the copy direction. Yes?
I think I understand the logic you're using.
Yes.
I think it's very beautiful and very interesting.
Thank you.
I'm curious.
Uh-huh.
The assumptions you're making about probability of copy in one direction as opposed to another,
Mm-hmm.
based on accuracy, based on shared flaws and
Yes.
things like this.
Yeah.
Have these assumptions been statistically validated, or are they under testing at this point?
So we have tried it on some data sets, and I can present the experimental results in a moment. Yeah. So I guess I will skip the formulas, but basically we capture these intuitions using some Bayesian analysis, and our goal is to compute the probability of independence and dependence conditioned on our observation, and these two probabilities should sum up to 1. According to the Bayes rule, we need to know the inverse probability, the probability of the observation conditioned on independence or dependence. And if we assume the copying on different data items are independent of each other, then we can compute the probability for conditional probability for each particular data item. And I will skip the analysis here. But basically, for different copying directions and for independence, we will compute different probabilities. And that's how we decide whether there is copying and what is the copy direction.
They're not independent.
They're
They're not independent, right?
They could be independent.
So you're saying, let me try to understand. So you're saying independence here means whether I copy one tuple from you has nothing to do with whether I copy some other tuple from you.
Oh, that part of independence. Yeah, it may not be independent, and there could be correlated copying, and I will talk about that soon. So far, yeah. So far, this has the assumption that the copying is independent. on different data items.
So the example I described is
Yes, yes, yeah. Okay, so for our example, we see that S3 shares data, some mistakes with S1, and shares some mistakes with S2, so that's how we detect the copying here. And S4 shares some common mistakes with S3, and that's how we decide the copying there. But just for correctness of the data so far, we don't have enough evidence to say which one is a copy or what is the copy direction. And so this is the core idea where we consider the correctness of the data for copy detection. We extend it in two ways. First, we consider additional evidence such as the formatting of the data and the coverage of the data. In our example, we see the inconsistency of how S3 formats the author lists. And so we suspect S3 is more likely to be a copier of S1 and S2. And on the other hand, we see that S4's author lists are sub-values of S3's author lists. So we think S4 is more likely to be a copier of S3. And second, as Bill just asked, so in reality, the copier may not copy independently on each data item. And it might copy an object and then copy the attribute values for all of the attributes. Or it might focus on a couple of attributes and copy all values for all the objects it provides. So we call it by object copying or by attribute copying. And we can leverage this correlated copying to improve our results. So for example, here I'm showing two examples. In both cases, we have 5 objects, 1 key attribute, and 4 other attributes. Here, S indicates the two sources provide the same value, and D indicates the two sources provide different values. And in both cases, the two sources share 17 same values and provide 8 different values. But they actually give us different confidence about the copying. We see that here, the two sources share all of the attribute values for objects 01, 2, 3, and provide a lot of different values for another 2 objects. So we are more confident about copying in this example. And here, the shared values are dispersed for different objects, so we are less confident whether this is copied or just happen to share some values. So we capture this extensions again using some Bayesian analysis. And on the other hand, we also consider the updates of the data, and we use HMM model to do the reasoning. So far, all the analysis is between a pair of sources. So it is local detection. On the other hand, as we said, there can be co-copying and transitive copying. To distinguish that from direct copying, we want to do some global analysis. And let me just show you an example why this is hard. And here, basically, I'm considering 3 examples where in all of the cases, S1 provides values V1 to 100, S2 copies V1 to 50 from S1, and V81 to 100 are popular values. In the first case, S3 copies 51 to 100 from S1. S2 provides 101 to 130 independently, and S3 copies that from S2. So it is multi-source copying. In the second case, S3 copies V21 to 70 from S1, so it is co-copying. In the third case, S3 copies V21 to 50 from S2 and independently provides 81 to 100 as they are popular values. So it is transitive copying. If we do local copy detection, we actually got exactly the same results for all 3 cases. And we even compute the same probabilities for all 3 different cases, because typically when 2 sources share a lot of data and one copying is likely, then we are likely to compute a very high copy probability. So in this case, or 1. And how about if we count the number of shared values? That might give us some clue. But it doesn't work here because the same number of values are shared between each pair of sources. How about if we examine and compare the set of shared values? Again, it doesn't work because V21 to 50 are shared among the three sources in both cold copying and transitive copying. So just reason about some aggregated information is not enough. And we have to reason for each data item in a principled way. I don't think I will have time to go through the details, but the basic idea is we want to find a set of influential copying relationships that influence the rest of the copying relationships most, because transitive copying and co-copying can typically be inferred from direct copying. And then for each of the rest of the copyings, we reason about the probability of copying conditioned on this set R and decide if it is still direct copying or indirect copying. So I will skip the details here. And here is our experiments. So recall that we found these copying relationships, and we call it golden standard. And we actually generate a silver standard because we cannot crowd data from two of the sources for business reasons or technical reasons. One of the sources sell their data. And so we generate the silver standard, and we compare our copy detection results with their results. And we measure precision, recall, and F measure. Precision measures among the detected copying.
Sorry, I missed where you're getting ground truth here.
So we look at their websites to find explicitly claimed clients, resources, and partnership. And we also check their code to find citations. That's
And how many cases where you found a site actually copying from multiple sites in that directory?
so this source copies from this source, and this source copies from both. So here there are some cases where we do not know the copying direction. And we see transitive copying, we see some co-copying, and we see multi-source copying. Yeah. So there are in total 11 copying relationships. And we detect the precision, recall, and F measure. And among the 11, we are able to detect 8. And on the other hand, we detected 3 extra copying relationships. So both precision and recall are 0.79. And this is global detection. And if we only do local detection without worrying about co-copying and transitive copying, then we could have a low precision. And if we do not consider correlated copying, we actually have a very low recall.
Then this is precision recall over the number of items?
The precision is among the detected copying, how many are correct? And the
at the
recall.
item level?
No, source level.
Just at the sources. So
Yes.
this is 80% of the
That's true.
images in this graph.
Yes, yes, exactly. Yeah. Okay. So now let me talk about the applications of data integration in data integration. So when we integrate data from multiple sources, we face 3 challenges. The first challenge is that 2 sources can describe the same domain using different schemas. This is like when 2 persons organize their stationary drawer, they can organize the same things in completely different ways. And so we want to find the one-to-one mapping between the different elements from 2 sources and to resolve such structure heterogeneity. Second, 2 sources can describe the same real-world entity using different attribute values. And this is like one person can call this paper cutting tool scissors, and another one can call it paper scissors. And to resolve such instance heterogeneity, we want to be able to reason that scissors and the paper scissors actually refer to the same real-world thing. And finally, two sources can provide conflicting information. This is like one person can call this scissors, and another one can call it glue. So we want to figure out whether this is scissors or glue. We want to resolve the conflicts and find the truth. So far, the existing solutions for all these challenges all have an important assumption that all the data sources are independent of each other. However, if we consider the copying of the data sources, we can add a new dimension to various aspects of data integration. First, for resolving data conflicts, we can improve truth discovery by thinking about ignoring the copied data. And also, we can integrate the probabilistic data by removing the unrealistic assumption that data sources are independent. To resolve instance heterogeneity, we can improve record linkage by being aware of the copying. And also, we can distinguish between wrong values and alternative representations of the true values to improve record linkage. Third, for resolving structure heterogeneity, we can optimize query answering by ignoring some of the copied data copiers or by ignoring some of the sources that are widely copied. And also, we can improve schema matching. And finally, we can recommend trustworthy, up-to-date, and independent data sources. So let me briefly talk about truth discovery. So consider an example where we have 3 data sources, each providing information, affiliation information for 5 database researchers. And we see some conflicts here. If we do a naive voting to resolve the conflicts, meaning that we take the value provided by the majority of the data sources, we can actually do pretty well. For 4 out of 5 researchers, we are able to find the correct affiliation. By the way, notice that S1 actually provides all correct values here. However, now consider if we have 2 more sources that copy the data from S3. Then if we still do a naive voting, S3's data would dominate the results, and we will make mistake for 3 out of 5 researchers. So recall that we just said sharing a lot of false information is a strong indicator of copying. But as this example shows, in practice, we often do not know which values are correct and which are incorrect. And this becomes extremely tricky when we have copiers. And our solution starts with copy detection by assuming each value has the same probability to be true. So in this example, in the first round, we will compute a high probability of copying between S3, 4, 5 because they share almost all of the data. And we also compute a fairly high probability between S1 and S2 because they all also share 3 values. And then, according to the detected copying, we can rethink about the voting. And here, we want to ignore the copied values. And for this example, consider voting on the affiliations of McCarray. And here, each big circle represents a value. And the larger the circle, the higher the vote count. And each small circle represents a data source, a provider of that value. And the larger the circle, the more accurate is the data source. So we see that at the beginning, BEA still wins the vote. However, its vote count is not 3 anymore. I will skip the details, but basically S4 and S5 can copy the data from S3, so we discount their vote counts. Then, according to the voting results for all of the data items, we can compute the accuracy of the data sources. In later rounds, for the data sources that have a higher accuracy, we will give them higher vote counts. And on the other hand, we can also recompute the copy probabilities. So in the second round, actually, we already compute a much lower probability between S1 and S2 for copying because the three values they share are all correct values. And we can see that we gradually compute a higher accuracy of S1, S2, and a lower accuracy of S3, 4, 5. So starting from round 4, because we already have a higher vote count for UCI than for BEA and AT&T. And this trend continues until round 13. We compute 0 probability of copying between S1 and S2. We compute a nearly 1 accuracy for S1, and we are able to find the correct values for all of the database researchers. So note that there is an interdependence between choice discovery, between copying detection, and between source accuracy computation. We solve this problem by iteratively conducting copy detection, choice discovery, and accuracy computation until the results converge. We can prove that it definitely converges if we skip the accuracy part. And if we do consider the accuracy, then our observation is that it will converge when the number of objects is much higher than the number of data sources. So this is how we find the correct values at the time when we also detect the copying relationships. Note, however, that this is an offline process, but so it is not appropriate for the web data, given the sheer volume of the data and the frequent updates of the data, especially for choice discovery. So our question is whether we can discover choice at the time when we answer a query. So for this purpose, we proposed the Solaria system, which do online data fusion, online choice discovery. So let me use this example of answering the question, where is AT&T Shannon Research Labs, to illustrate this system. We see 9 data sources providing 3 different values, New York, New Jersey, and Texas. And as Solaria's probe each source, it returns the current answer according to the probed data. It also returns what's the probability that this answer is true, and what is the probability range, the minimum and maximum probabilities. And then when it probes more sources, it updates the answers. And we see that at the beginning, it returns a wrong answer, Texas. But when it sees more sources, it changes to the correct answer. And the probability of this answer increases gradually. And as we also see, after we probed 8 sources, we are already confident enough that New Jersey must be the correct value. And at this time, we can terminate, even without probing all of the sources. So there are several challenges in building this system. First, we want to quickly find the answers as we probe new sources. And second, we want to be able to compute the probabilities and quantify our confidence. Third, we want to order the sources such that we can return correct values as early as possible and terminate as early as possible. And we actually show that this becomes extremely hard when we consider the copying between the data sources, because when we probe a copier before the original source, we don't know if they share data, and we don't know whether we should ignore the data. So I will skip the details here, but if you go to VLDB, you are welcome to go to, I think, the Thursday session about data integration to check out the details. Okay, so next, let me show you a demo of the system. So as we have seen at the beginning of the talk, This is the Solomon project and Solomon system, and the entry page is a map of the data sources. And here we use the data sources extracted from AdBooks online bookstore aggregator. And let's consider 3 scenarios. In the first scenario, let's assume you are a data analyzer and you want to understand the quality of the data sources and the copying relationships between the data sources. So here from this map, you can see that for each node represents a source, and the larger the font, the higher coverage of the source, and the darker the color, the more accurate is the source. You can also search the source by the quality measures. For example, we can search large data sources, and here it returns 6 of them with coverage larger than 0.5. And we can also see from this table the other quality measures. We also see from this map that most of them are in this department area country. Actually, for each data source, we can click here and see some visualization of their quality measures. For example, here we see a churn phase that is quite friendly, showing that this is a good data source. But if we look at this, we see a kind of evil churn phase, and this is because it has very low accuracy for the data. We can also search the data sources by their name. For example, I could search textbook stores. And here we see there are 16 results on the map. A lot of them, as we have seen, is in this textbookistan country. But on the other hand, textbook stores do not have to copy from each other. And so we also have some of them in some other countries. We have some in the islands. And we also have some off the map because they are independent. We can also search some particular bookstore, such as the book.com. So here we find 3 answers. And the book.com, free postage at the book company, and free US air shipping at the book company. And so they are these 3. And intuitively, this seems to be 3 different accounts of the same bookstore. And actually, we do find the copying of the data between free postage and the book.com and free air shipping and the book.com. And if we click on one of them, we can see more details. So here it shows that it copied this many data items. The copy probability is 0.5 in each direction, and these are the copied data items. And we note that we didn't see copying between these 2 sources. And if you wonder why, we can search the copying relationship, the book.com and the book.com. And here it shows 3 pairs. For this particular pair that we are interested in, we can click on it, and it shows that they are independent and they share very few common values. And that's the reasoning. And actually, we found they actually had 0 overlap. So that's also the reason why we are not sure of the copying direction. So we don't know if these 2 sources split data from the book.com or the book.com actually union the data from these 2 data sources. Okay, so now let's suppose you are a data provider and you want to find out who have copied data from you. So you can search your own bookstore name. Here I'm using Hippo Books. And for this one, we can see the quality measures, and we can see the copiers, direct or indirect copiers. And one funny thing is, I mean, here is Hippo Books, and on the other hand, we have O's Books and Beagle Books. So it's kind of animal bookstores, animal world. And if we click on one of them to understand what's happening and why copying is considered as likely. We can again see the details, and here we show the explanation for our Bayesian analysis, Bayesian reasoning. And if this is too long to read, you can see a visualization of the reasoning. So here each square represents a data source. The overlapping area represents the shared books. And here we have 3 squares. The inner square shows the data items on which they provide the same value in the same format. The middle square shows the items on which they provide the same value in different formats. And we divide the popular values and unpopular values. And the outside square shows the data items on which they provide different values. So we see for these 2 sources, among the overlapping data items, for a lot of them, they provide the same value using the same format, and there are some common mistakes shared between them, and that's why we conclude with copying. And
Sorry, how do you see the direction there?
Yeah, that's a good question, and I forgot to say that. Note that this color represents the quality or some quality measure of the data. And so we see these 2 sources have very similar quality. And that's why we actually do not know the copying direction. Yeah. Okay. In the third scenario, let's assume you are just an information user and all you are interested in are about the books. And you can search some particular books. For example, I could search, let's say, software security. And here it returns all of the software security books. And actually, if I click on one of them, I could see copying on this particular book. So how the information is propagated for this particular book. And if you are wondering why this author list is considered as the correct author list, you can click on the question mark and ask for explanations. So here, this is the same like big circles and the small circles you have seen in the talk. And note that for example, this blue circle corresponds to the correct value. And we see that it has 5 providers. But there are some other values. For example, this has only 2 names instead of 3 names. It is provided by even more sources, 8 sources in this case. And the reason we still consider this value as correct is because this value is among the providers, 6 of them are copiers. So we discount the vote counts. So here the vote count is only 11, and here the vote count is 17. Okay, so this pretty much finished the demo. And there have been a lot of copy detection work for texts, for software programs, for images and videos, and for structured data sources. We have given a tutorial about all this in this year's SIGMOD. And also our work seems to be very relevant to data provenance. But there, they assume the knowledge of the provenance and the linkage information and study how to effectively present and retrieve such information, whereas we are trying to detect such information and apply that in various aspects of data integration. Several takeaways. Oops. Copying is common on the web, and it can be detected using some statistical approaches. We can also show that knowing the copying relationships can actually benefit the various aspects of data integration. So this concludes my talk, and I want to say thanks to all the contributors to this project. We actually found that all of the people have spent more or less time at AT&T, ranging from 35 years to possibly 35 hours, including our own Alon Halevi. And here I'm ranking them according to the time they have spent at AT&T. Okay, thank you very much, and you are welcome to try our demo. Yes?
Could you say a little bit more about the scalability of your approach? If I really want to run it on the web or maybe
This is a very good question, and we are actually, so first, so the scalability is not a big issue for large data sources because we can always sample data. But on the other hand, when we have like thousands or like millions of data sources, if we need to reason about every pair of sources, that can be very expensive. So far we are studying how we can make the technique scale. Yeah.
Going back to the
Yes?
ground truth, I guess I don't quite see why you have ground truth of negatives. You have ground truth of positives because someone said, I copied from this person, and I say that I announced that on my website. But no one's going to announce, I did not copy from this person.
So yes, this is a good question. So basically, as far as there isn't any claimed copying or like resources or clients, we consider there is no copying. And we know this is not perfect, and we try to call them or email them and asking some questions about this. But you can imagine, I mean, nobody really wants to answer our question, or they just say,
Right.
all the information is on the web, and you can only check the web.
So that's fine. But the difference between global and local mainly was in the precision, not the recall. And that would mean that you're, like, I may be completely driven by the fact that there's going to be no copying, and you might be, your local algorithm might have actually found actual copying.
Yes.
Announced.
Yes, yeah.
The global method looked better because it didn't find that, but actually might be doing worse.
So actually, not really, because I mean the local method it returns about like a lot of copying relationships, and you are very sure that some of them are transitive copying.
Okay.
Yeah.
So specifically because of transit.
Transitive copying or co-copying.
The other thing I'm a little worried about with the example you have is that the weather data, there's essentially two sources for it in the U.S. So everybody copies from everybody. There is no independent source weather measurement system to some approximation. So the graph that you the graph that you got from ground truth, you should see. I mean, you can trace it back to the 2 or 3 forecast models that are running, and that's it. Everybody gets all their forecasts from there.
So the funny thing, yeah, that's a good question. The funny thing here is that although you see that all of the sources derive data, I mean, eventually from weather.gov, their data can be actually very different because they apply different models and they show very different values.
So while the source is quote, the source of the data is these a couple models, they've done enough transformations on it where now
That's true. That's true. Yes, yeah, we don't call copying in that case.
That seems right.
Yes.
Okay.
Yeah. Any other question?